Hello everyone, this is Dr. Ross and this will be a short video on how to combine errors when making measurements using analog tools. So I'm going to start sharing my screen and I'll pull up a Word document that I will annotate on. So I've already got the title, Combining Errors When Performing a Titration. This is something that you can often do incorrectly and I want to address this before negative things start to happen. So let's say we're going to do a titration. So what's important in the titration in terms of error is going to be the initial and the final measurement. So let's say, for example, that you've already inspected the buret and the absolute uncertainty is plus or minus 0.01 milliliter. I won't go into too much, well, I won't go into any detail in this video about what absolute uncertainty is. That will be in another video, but you're very welcome to look at that video before watching this video. So if you haven't already looked at absolute uncertainty, pause, go back, look at the absolute uncertainty video. So let's say we know the absolute uncertainty in our buret is plus or minus 0.01 milliliter. And let's say we measure an initial volume of 2.54 milliliter. And we measure a final volume, hopefully at the equivalence point, if we've done it correctly, of 26.39 milliliter. So we've got a volume difference of the final value minus the initial. We have to preserve two decimal places. So this would be 23.85 milliliter. Okay, so we've done all that. Everything looks great. What about the uncertainty? How confident are we in the measurements? Well, uncertainty occurs not just in the change in volume, but it occurs in the initial measurement and the final measurement. So uncertainty occurs with both the initial and final measurements. So in other words, i.e., we know that initially we had 2.54 plus or minus the absolute uncertainty, which is 0.01 mil. And we have the final measurement, which is 26.39 plus or minus the absolute uncertainty in that measurement, which was plus or minus 0.01 ml. So importantly, we need to discuss in this video whether the absolute uncertainty applies to the delta V or just the individual V's. Okay, because this is often overlooked. So there's a rule that applies when you add or subtract measurements. So there's a rule that states when adding or subtracting, components, so I'm going to say X and Y. Y, X, and Y, they're just labels, and I have two of them because I have an initial and a final volume. I could have more labels if I had more than two variables, but it makes sense to just stick with two. So when adding or subtracting components X and Y, the combined uncertainty is the change in X squared plus the change in Y squared, and then we have to square root the whole thing. So in this case, in our case, the combined uncertainty is going to be our absolute uncertainty, which is 0.01 mil squared for the initial value, and then again 0.01 mil squared for the final value because it's the same tool being used. Then we have to square root that, and that would give us approximately to the degrees of accuracy I'm allowed to give. So to a second decimal, I'm approximating because the real value is going to have extra values that I have to round. So it's approximately 0.01 ml. So in this case, it looks like my absolute uncertainty is the same as my combined uncertainty, but in general, they're not the same thing. So I would say here, my delta V, remember, we had up top here. So in this case, I'd say my delta V is 23.85 mil. So 23.85 mil plus or minus the combined uncertainty, which is about 0.01 mil. Okay. But I caution you, although it looks like it's the same in general, so this will be a caution, the combined error of more than one measurement is not always numerically equal to the absolute uncertainty. So be very careful. It looks like it is here, but I'm going to give you another example now where we can flesh out that it's not always. So let's look at a second example. So let's combine errors when measuring volume with a graduated cylinder. Okay. So combining errors when using a graduated cylinder, which is something that you often do in a lab. Okay, so let's have a look at this. Let's say on this occasion that the absolute uncertainty that you've ascertained is plus or minus 0.2 mil. Okay, let's say we have an initial measurement of 2.6 ml, and we have a final measurement of 31.2 ml to give us a change in volume of 28.6 ml. Okay, so let's do the same rule is going to apply because we're adding or subtracting. In this case, we're subtracting. So we're going to have to take the change, the uncertainty in the first measurement, square it, the uncertainty in the second measurement, square it, add them together, then square root the whole thing. So the combined uncertainty in this case is going to be the uncertainty, absolute uncertainty, which is plus or minus 0.2 mil. We're going to square that for the initial value. We're going to do the same for the final value. We're going to add them. I'm going to take the square root of the lot. On this occasion, and I'm saying approximately equal to because we have to round because we're only allowed to give one decimal. So rounded, it becomes approximate, and this is approximately 0.3 mil. So here you can clearly see 0.3 is not the same as 0.2. So that general principle that we saw earlier, that my caution, that the combined error is not always equal to the absolute uncertainty, here it's very obvious that that's not the case. So in this case, we would say that delta V is equal to the average value, which was 28, sorry, the average, was the value that we calculated, 28.6, plus or minus the combined uncertainty, not the absolute uncertainty of the measuring tool, which was plus or minus 0.2. So clearly it makes sense to take as few measurements as you can, because every time you make a measurement, you're going to add those uncertainties together if you're adding and subtracting. And so the more measurements you have to make, the greater the opportunity for error to creep into your measurements. So I would say the take home of this video that I want you to be aware of is that error is not always equal to the number, is not always equal to the absolute uncertainty, and therefore, if possible, minimize the number of measurements needed. So if you can make 2 measurements and get the same answer, or you can make 5 measurements and get the same answer, 2 measurements is always going to be better than 5 in terms of your confidence in the outcome. Okay, and that will be the end of this video.